first episode on nature of science. Science concepts everybody should know. I'm Mr. Kermer. You can see I've solved my lighting problem that I had in the first two videos. Sorry about that. Kind of had a halo behind me. Hopefully that it'll be better. This one I'm dealing with part 3 on nature of science, which I'm going to call sort of advanced inquiry and studies, just to give the senior students and maybe adults that are interested in science a little bit more in terms of the way it's done. Some more information about that. So here's a situation. Let's say that I have an object in this box. I'm serious, you can hear there's an object in the box. And I ask you to try to figure out what this object is. But you're not allowed to open the box. Under any circumstances, you can't open the box. So what we need to do is we need to experiment on this from the outside, right? I can shake it, I can listen to it, I can roll it around, see if it rolls or slides. All sorts of different ways I can come up with an idea of what I might think is in the box. Then I come up with a hypothesis of a conclusion of a bunch of different little experiments of what I think is in this box. But because I can never open the box, the other thing I can do is maybe compare that to conditions I know. So I could get a box that's similar and start putting in objects that I think it might be and comparing the two of them, because I can never open this box. Why do I give this analogy? Because in science we have that problem often. We might have the structure of an atom. We can't see an atom, but we want to know what it looks like. Right? It's too small to see. We want to know what the surface and the inside of the sun is made of, and we can't go there. So we have these situations where these called black box experiments, where there is a box that we just simply can't open. It's a mental idea that we just can't actually get to it, but we have to solve it somehow. So we often do, in those kind of instances, we do this idea. We'll take comparatives, so things we can control, boxes we can control, the things that we can put in there we can control, and we can experiment and compare the results to these two things. Do it with this, do it with things that we know, and when we eventually get them to be sounding and behaving pretty much the same, then we can summarize that we must know what's in the box, right? And we know what an atom looks like because of that, because we've done similar experiments. Those are difficult concepts to deal with, but that's how they're approached. And again, through repeated experiments done over and over again, we then narrow down what we think these things must be inside that box, if you will, or the conditions. So that's how we know what is in the center of the sun. We know what an atom looks like. All things that we could look up and talk about. And there's tons of science information that comes about that way, right? But it's not always practical to do experiments. So the other thing I wanted to talk about is this idea of a scientific study, right? For example, if I want to know what causes cancer, a specific kind of cancer, I know that there's a lot of variables that are going into an individual and groups of individuals in terms of things that could cause a cancer. So I might pick a specific variable that I'm using as my hypothesis. I think this is causing a specific type of cancer. But I don't really want to do an experiment. Right? I don't really want to expose people to this condition and see if they get cancer or not. And compare them to people who aren't exposed. So we often do it in a reverse way. We do a study. So we say, let's find people who are already, because of the job they do, or because of where they live, or whatever it might be, that have been exposed to this particular condition. And another group of people who have not, and let's statistically analyze. Let's put a number behind how many of these people are getting cancer and how many of these people are getting the kind of cancer I'm looking at. And if I see that this group is repeatedly getting cancer more than this group, then I can conclude that that particular agent is probably causing this cancer, or at least it's influencing it in some way. And that's all can be done mathematically. The math behind statistics is very complicated, but it can be simplified for us, right? We can compare it to something that we know. For example, flipping a coin, right? We can understand that this coin has heads and tails, and if I flip this coin 10 times, I should get 5 heads and 5 tails. But we also have to admit that there's it's a possibility, as small as it might be, that I could flip 10 tails in a row, right? So having too small of a sample doesn't necessarily show me that the probability of that is 50-50. So I don't want to have, and that's difficult because sometimes I might only find 10 people that have been exposed to this particular condition. And, I don't know if that's significant that they're getting cancer. So it's better if I have a larger group. If I flip this coin 100 times, I'm going to get closer to 50-50 because it's very unlikely I'm going to flip 100 tails in a row. Could happen, but it's unlikely. And if I be better if I had 1,000 flips. I'd get closer to that 50-50. Right? So in math, there's ways to calculate that out. And with percentages and the probabilities, so there's lots of ways to calculate that out. But what that ends up with is it gives us the odds of what something is going to happen. So in science, we use a lot of that math. And we often will end up with a study that will be with something tagged on the end of it that people don't look for. But you can look for this when you see a study. They also do it with like political surveys and everything else. It was all done with similar kinds of statistical methods. But the idea there is that if I come up with a specific amount, that I would say that that's accurate within 3%, 19 times out of 20. So it's a really complicated way to basically say that I'm admitting that there is this possibility that someone flipped the coin 100 times in a row and came up with the tails. It's possible, but it's because of the way I've done my experiment, it's highly unlikely. 19 times out of 20, I'm right within a narrow range. But there is that possibility that I'm outside of that range. And that's why studies become incredibly important to be duplicated and repeated, because Galileo set this out 400 years ago. If you want people to believe it, you tell them how it's done, and it should be repeatable. Don't believe me, try it yourself and see if you can get the same results. And here's where we have to talk about modern society and science and the counteraction between those two things. For up until the last maybe 20 years, science information was slow to filter out because it would have to maybe end up in scientific journals, we have be verified and put into all different places, and it's hard to read. And by the time it gets kind of simplified down into textbooks that you're starting to look at in high schools and things, the information is very valid. Nowadays, as soon as I finish doing my study or my survey, boom, I press send and it's out into the world. And it doesn't necessarily mean it's been verified. Even if I said that, it's just my experiment I did at home, right? I did my little experiment here with my golf balls and rolling down a ramp, and I click send and out they go. It doesn't mean that it's accurate at this point, right? And we have to be really careful with that, because science is like our knowledge and our ability to grab knowledge is moving faster than science can keep up. And of course, everyone wants to sort of discover something new, so it's not really fun to be the verifying scientist. Okay, I'm just going to take other people's ideas and make sure that they work. But there are some ideas that are important enough that we start to do that. So, but we have to be careful, right? Because just because the idea is out there doesn't mean that it's valid. And a great example of that was a study that was done on vaccinations and how vaccinations increase the chance of autism. It was a single study, it was done by one individual that put it out there right away. And in our modern society, it was picked up really, really quickly. No one had verified that experiment. So it hadn't had time to go through that process of Galileo, where we could try the same kind of experiments. The sample size wasn't large enough. When it was repeated, it's totally inaccurate. And everybody in the scientific community knows that that is totally untrue. And even the author of it has admitted that it was totally false, and he fixed his data. But yet that information is still floating around in the cyber world, and people still draw on that. So that's very, very dangerous. So what can we do? Well, as consumers of information, we have to be really careful about science information. We have to look at that with that little bit of an edge eye, but also the trusting or the knowledge that we can trust if it's come through this process. So the first thing we should be looking at is not if this is thrown out to us by the media, but what's the source of that, and has science process actually been working to get that information out? And it's fun to talk about studies that they do really quickly on social relationships and the cause of this and that, but it doesn't mean that they're valid. It's interesting to talk about, and it should spark conversation. But we should also look at the source, and also that idea that there is this, in every experiment, there's this room for error, that we may not be perfectly correct in what we've done, and it needs to be repeated over and over again before we start putting it into our general knowledge. So I hope that you have a little bit more insight about digesting the volumes of information that come to you from the scientific community and what they mean.